And welcome, Mindsetters. This is Learn Extra Live. Today we're doing physical science with Phil. Phil, how are you today?
I'm great, thanks, and you, Cardinal?
Good, thank you. Please tell us what we'll be doing today.
Okay, well, today we're going to be starting to take a look at vectors and scalars. Some of you might have done this before. For those of you that have, take some notes, and you guys have got exams at the end of the year. Everybody's doing this stuff.
Awesome. Awesome. So you guys know that you have to tune in. And if your friends haven't tuned in, tell them to join us too. You can go prepare your board, Phil, while I let you know where to get hold of us. So you already know our Facebook page is facebook.com/learnextra, and our Twitter handle is @learnextra. And since it's Tuesday, and it's a really awesome, warm Tuesday, we have some prizes. You know, there's the Casio calculator, as well as the labeler. This is to the best and most interactive mindsetter of the day. So make sure that you are that person. And thank you to Liberty. Liberty is always awesome. And as you guys know, my voice is a little husky today, so you're going to have to bear with me. And if you can't hear me, tell me on the page, okay? Because I will be on the page the whole show, and I expect you guys to be there with me. Over to you, Phil.
Thank you so much. Okay, well, Mindsetters, today we're going to be taking a look at vectors and scalars. Now, even the matrics should be tuning into this show. It's a section which haunts you all the way up into university unless you get it right, and it's not that difficult. So later on in the show, we're going to be walking around, and we're going to be walking in a different way than we've done before. Okay, so these words, vectors and scalars, looks a little bit scary, really doesn't have to be. Now, what we've done is that calculator, that label is up for grabs. What we've decided to do is we've decided to make a challenge for you guys. I've done this for the matrics before, and I want you guys to get working on this. So get pens, paper, start writing this down, get a calculator, some protractors, some pens, pencils, all of that stuff out, and I want you to take down this challenge question. Now, first person to put up this challenge question, I'm going to be asking you to look at the page very, very carefully. Make sure that you guys are answering this. Now, just a reminder of how the challenge question works. I'm going to put the challenge question on the board. We're going to be posting it up to Facebook. And the first person to get the answer right with the correct explanation will get that calculator. So let's put up that challenge question, and here it is. So we've got this person which is walking. Okay, well, this is slightly different to what we've done before. Okay, so we've got a person which is walking 40 meters south and then 30 meters east. Their displacement is. Now, this seems very, very simple. Okay? Now, for those of you that haven't done displacement before, this might seem a little bit weird. And for those of you that are just getting into this, this might seem very, very simple. Okay, well, I walk 40 meters, then I walk 30 meters. How difficult can it be? Now, the answer is not as obvious as you think because of this word displacement, and that's something quite weird. And here we go. We're going to be explaining today exactly what displacement is and how it's different to distance. Now, we've seen something like this before. We've seen 40 meters, and 40 meters gives us an indication of where we're going. Now, I want you to make sure that you actually notice what's going on with the units. Now, we've left off one of our units. I want you to try and spot what's going on. That's the first part of your challenge. So if I've got 40 meters south, I know where I'm going, okay? Now, there's a lot of information there. There's a number, there's a unit, and there's a direction. Now, the next time I say it, there's something actually missing here. I've got a number. There's something missing inside there, and I want you to guess what it is. And then east. Something very, very strange going on there. Let's see what's going on. Let's see what displacement, let's see what distance is, and let's see the difference between vectors and scalars. Now, if you pay attention during this lesson, you can manage to figure out what's going on with all of these. Two of these answers look immediately correct. I've walked 40 meters, I've walked 30 meters, and that means that I've walked 70 meters. But just to give you guys a little bit of a hint, the answer is not as simple as it seems. So that should be giving you a little bit of a hint as to how to do this. I want you to get on that page, start discussing it, start sharing your answers as well. Okay, so let's get into the lesson. Let's start to take a look at these words, and let's try and see what's going on. Now, the only difficult part of this section, I think, is the words. So each stage, I'm going to try and explain each word as carefully as I can. Okay? Now, what we're going to do is we're going to take a look at this word quantity. Okay? So quantity is just a little bit of a revision. You've done this before in grade 8 and grade 9. A quantity is something which I can measure. It's how much of something I've got. Now, there's something quite cool about quantities, is they've actually got a tiny little identifier attached to them. So I've got an example over here on the board which says a person walks 10 meters. Not a lot of information. We know that there's a person involved. We know that there's 10. And then there's something magical attached to the end of a quantity. So what I'm going to do is what we're going to explain here is that there are units attached to a quantity. There's usually a number which is attached as well, and now that introduces another word. Okay, now a lot of people, especially the grade 10s, they struggle with these words. Okay, and well, units, a lot of you leave these off. Those are very, very useful things. What units do for me is they tell me what is being measured. That tells me what I've got a lot of. So this tells me what I'm measuring, and the 10 tells me how much of it I have. And that is called my magnitude. So what I'm going to do is I'm just going to really highlight this, because this is something that the grade 10s, 11s, and 12s really struggle with. This word magnitude is something that I really don't use in everyday life. It's something which is quite uncommon. The magnitude is how much of it I've got. So this is telling me I've got meters. So I've got distance. I've walked somewhere. 10 is telling me how many meters I've got, how many meters I've walked. Might seem a little bit simple, but the only reason that I'm starting simple is just to make sure that everyone is with us and that you guys can actually follow through and there's no problem so far. Okay, so just to revise, a quantity is something which I can measure. So that's something from grade 7 or grade 8, right? I know that I can measure a quantity. Two very important parts of any quantity, doesn't matter what type it is. I've got a magnitude, which is how much I've got, and then I've got units, and these tell me exactly what I've got. I cannot emphasize this enough. Please, every time you write down a final answer, you must give me the units. Now, your teachers are probably saying, okay, the units, and you're just saying, the number is fine. The calculator gave me a number, and that's everything. Well, if I tell you that you've got 10, the really strange thing is, okay, I've got 10 what? Now, over here, this identifies what I've got 10 of. It might not seem very, very important until you start dealing in currency. Now, if I walked up to you and I said that I've got 10, and well, you say, okay, well, I've got 10 what? Okay, I've got 10 rand. Great, I can buy something small. Okay, what happens if I've got 10 million? 10 million what? Well, if I've got Zim dollars, sadly, those don't work anymore. But you'd be quite upset if I gave you 10 Zim dollars, because that wouldn't be worth anything. It's quite important to know what you've got. Okay, it's absolutely vital that I need to know what I've got. Okay, so there we go. So quantities, something I can measure. I've got to have a number which tells me my magnitude. Good word, just write it down, please. It's how much you've got. It's the size of the number. And then my units is what I've got. Well, let's start investigating some interesting quantities. Well, I bet you've never paid this much attention to quantities before, but I'm going to be bringing up some really, really complex words. I've highlighted them over here. Now, this word scalar. Now, it kind of sounds a little bit similar, but is not quite the same as a scale. Now, anything which can be scaled can be measured. Now, this is something quite interesting. This is my first type of quantity. A scalar is a measurement that only tells us the magnitude of something, so how much I've got of it. All scalars do have units because a scalar is a type of quantity. Now, let me just make that clear. A scalar is a quantity, but now it's limited. I just want to show you just how limited it is sometimes. So a quantity, that means that it's got a unit, it's got a magnitude, it tells me how much of something I've got. The problem is that scalars can be great for some things, but for some things they're not sufficient. Now I'm going to give you a few examples as to where a scalar is actually going to leave you in trouble and where we need to take over with a vector. Sometimes a vector is better, sometimes a scalar is better, sometimes you have no option. So now a scalar only tells us the measurement with the magnitude, and that's very important. A scalar only has magnitude. It only tells me how much of something I've got. Now, what I'm going to do is, each time I give up one of these examples, I'm going to be scribbling all over the board. So I want you to listen to me very carefully, write down what I say, and then hopefully get into some of this stuff. So magnitude, again, is how much of something I've got. Now, what I'm going to do is I'm going to write down a couple of scalars, and I want you to start matching a pattern to all of these scalars. I want you guys to discover. Now, the problem with teaching is it's great when I talk and you seem to be understanding everything, you're writing stuff down, what I'm saying. The problem is that you need to actually start discovering stuff for yourself. Otherwise, you're not going to remember anything. So now, if I've got a magnitude of something, what we're going to do, and I like the word magnitude here. You're going to hear me say it 1,000,000 times today. Well, let's give you a few magnitudes and units, and you tell me what these things have got in common. Well, let's start dealing with some stuff, right? I gave you an example a little bit earlier. 10 that means something. 10 kg, that means something. 10 that means something. Now, from looking at these, it's quite difficult to tell what I'm looking for. What I need to do is I need to realize is that I've got a magnitude of 10 in each case. So that magnitude over there, I've given you 3 magnitudes. I've also given you 3 different units. The reason that the units are so important, because that tells you what you've got. So I've got 10 m for meters, 10 kg for kilograms, 10 s for 10 seconds. These guys have all got something in common, apart from the fact that they're 10. I want you to ignore the 10. There's something else quite special about these. I've only got the magnitude. Now, what else can these actually give you? Well, it's going to become clear as we start moving through this. So that's what a scalar is. Let's see that we've got an example. So I've got an object which has got 80 kilograms of mass. Let's just point out the bits and pieces which we can find out about the scalar. Again, a scalar is a quantity. So let's figure out what we've got. So the object's mass cannot have a direction. Now this is something quite limiting, and you might say, okay, well, of course it can't have a direction. Now this is where we start to bring in something called vectors. Now, if that's not immediately clear, just stick around, start writing down what we're saying. Okay, now I've told you about this object with 80 kilograms of mass. The nice thing about it is it will have the same mass everywhere. You cannot put a mass in a certain direction. That's movement. Now, a mass does not have a direction. This is why I say some things are scalars, some things are vectors. Some things you can't choose. I cannot choose for mass to become a vector. Now, if you don't know what a vector is, it's coming right up. So this object cannot have a direction. It's absolutely important that this idea of directions and quantities starts to come into play. And it's the same anywhere. Scalars are the same all over the place. Doesn't matter on anywhere on Earth, scalars are going to be exactly the same. Okay, so let's start moving a little bit further than that. Now, that this object cannot have the mass is quite important. Now, how can we introduce this idea of direction? Let's actually move that out of the way so we can actually start to introduce something else which does have a direction. Now, most of you that have done grade 9 and you've started dealing with mass, force, energy, power, knows that there's a difference between mass and weight. Now, most of you are screaming at me saying, okay, well, 80 kilograms, I can change that into a force. I can find out how much force there is on 80 kilograms of mass, but it depends then on where I am. Now, 80 kilograms is something which would stay the same on Earth, on Jupiter, in space. It's exactly the same. What I'm going to do now is I'm going to try and figure out what about weight. Weight does depend on where you are. So now what I'm going to do is I'm going to change that into a quantity. And that would be 800 newtons of weight. Now you might say, okay, well, where's the direction for weight? Well, you try throw something up. What immediately starts to happen? What direction does weight always act in? All of a sudden now we've got a quantity which requires a direction. And that's where we come in for the need of vectors. Okay, so now other examples of scalars, things which do not have direction. Okay, well, distance, speed, and time. Now you might say, okay, well, these sound very familiar because I've been calculating these in maths probably. So distance, speed, and time. I've dealt with these before. Okay, well, distance just requires us to measure things in meters for it to become a distance. So there we go. There's my distance in meters, my speed in meters per second, or we could even measure if you're inside a car or a vehicle, you can say kilometers per hour. Now you're going to see me change the units very, very slightly. The reason that I've written it with a slash is because some people haven't done exponents in maths yet, and I want to introduce you to that very, very slowly. Time is probably the easiest one, and time is measured in seconds. Now, in physics, in chemistry, it doesn't matter. Time is always going to be measured in seconds when you're doing calculations. Okay, well now, these don't have directions. These are just magnitude and unit. Well, let's start dealing with this thing called a vector. Okay, now, I've started to introduce it in some of the sentences that I've been talking about, but there it is on the screen. A vector is something that has got magnitude, of course, because it's a quantity, but here's the big thing. It's got a direction. It's absolutely vital that you know that all vectors have a direction. Now that makes it a little bit tricky to answer vector questions. Vectors mean that I've got to add a direction at the end of each answer. I don't want you to just put the number, just put the units. and just leave it there, because usually when you're doing vector questions, don't forget about the direction. Please, 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 I can't emphasize it enough. That direction is absolutely important, because that's what makes this a vector. So it is also a quantity, so it's something which I can measure, but the big difference from a scalar is that a vector is something which has got direction. Now you might say, okay, well, what's the point of direction? Well, if I was to tell you how to get to somewhere, directions are very important. If I was to tell you to drive, okay, well, 100 meters. Okay, all right, so we're moving 100 meters. The question is in which direction? So 100 meters south, 100 meters north, all of a sudden we've started to make vectors. Vectors in many ways can be much more useful than scalars. Well, if I was to tell you that I was being pushed, for instance, if I was being pushed from the bottom, from the top, from the front, from the back, that would be quite important information to know. What would happen if you changed into the wrong gears inside a car, a taxi, or a bus? Now, what has to happen is inside, our gearbox decides our vector direction. That's quite important. Going forwards or going backwards is quite a big difference. Direction is everything when you start to deal with vector quantities. Absolutely important that you know the difference between a vector and a scalar. They're going to ask you these definitions. It's quite important to know. Okay, so now a vector has this direction. So, and a lot of you are saying, okay, well, so what? Well, as I said, when you start traveling, especially when you're traveling, there is our example. We've got a whole bunch of information. We've got 80 as our magnitude, kilometers as our units, and we've got a direction attached to there. So that's something quite vital to know. I need to know that I've got, okay, so there we go. Let's just move that around. Okay, so I've got my units over there, and it tells us what's being measured. What else is there? Well, I'm actually going to add a few notes onto this. Some of you might not be used to your cardinal points or your compass directions. So there's your first one. Okay, so that tells me where I'm going. So therein is my direction. That's hugely important because this identifies this as a vector. Okay, what's going on over there? There we've got our magnitude. You're going to hear me say that word so many times today. You're going to get sick of it, but you're going to know it. So my magnitude, my direction, and my units. This is a great way to answer a vector question. How far did I go? I went 80 kilometers. Where did I go? I went east in the process. So that means that I now have a vector. Now, vectors are a little bit tricky. The problem is there's many, many different ways of giving this direction. And as the show goes, what we're going to do is we're going to slowly decode it, slowly make things happen, and slowly help people through all these questions. So, what we're going to do is we're actually going to start off with probably the simplest way of giving directions. Now, this doesn't always apply. Now, some of you at home are probably saying, okay, well, what are cardinal points? Cardinal points is a bit of a weird thing. So what I'm going to show you now is how we work out those cardinal points. Most of you have seen the compass points before, and those are cardinal points. So what I'm going to do is I'm going to start off with these two crosses over each other, and we're going to put in our cardinal points. So if I've got N for north, E for east, and S for south down at the bottom, and then finally west. The problem with this is sometimes we're not actually given compass directions, and that's going to make things tricky. Now, I just want to leave on a little bit of a hint before we go to an ad break. Our challenge question does use cardinal points, but it uses something else. You're going to need to take a look a little bit after the ad break, but I'm going to leave it there. What do you think?
Yes, let's just go for a quick break. I just want to remind you guys about what Phil said. You need to substantiate. You need to tell us why exactly you choose the answer that you choose. Because I can just see A, B, C, D, E, F, G. Let us know why you're choosing that, because that's how we know that you actually understand.
And you're helping others.
Yes, and you're helping others understand it further. See you right after the break. Welcome back, you awesome mindsetters. So as you know, we're doing physical science for grade 10s, and we're doing awesome vectors and scalars, and I know that you guys are already saying you're having an awesome show. So make sure that you don't move throughout the whole show, because it does get more awesome on Learn Extra Live. You know that by now. Over to you, Phil.
Thank you so much. Well, I see a lot of you are making guesses on the page. I just want to reiterate what was said before. Guys, please, please, please. You've got to explain how you got to your answer, because a lot of you are just throwing the numbers out there. We're not going to give you those calculators. You guys have got to help each other. You've got to learn more and learn extra. Actually, I want to make sure that people are understanding what I'm meaning by substantiate. Okay, you've got to explain how you got to your individual answer. So, guys, stop throwing those letters around. It's not going to help you, and it's not going to help anyone else. We want you to explain step by step how you got it. And then if somebody gets it right, great, explain it to them. Okay, so all will be revealed. Okay, but before we get any further, what I'm going to do is I'm going to show you how to use the cardinal points. Now, I said to you that the cardinal points, the compass points, these are a little bit limited. The problem is that the cardinal points are actually different depending on where you are. And it also depends on you knowing where north, east, south, and west are. Now, that's a bit of a problem. Now, inside this building, I can't see the sun, I can't see the outside. I think I'm looking in a certain direction, but I'm not actually. And the problem is that it's very, very difficult. Now, let me tell you what a lot of learners start doing, and it's not correct. I can't assume that east is always to the right, because here's the problem. At the moment, my right is over there, and it's your left at the moment on the screen. And as soon as I start turning around, what I'm actually doing is I'm moving east, and that's not correct. You cannot move east. East is a certain direction on the planet. You can't move it unless you're moving around the planet and you're not Superman. Okay? You may think you are, but you're not. Okay, but what I want to emphasize is that cardinal points are a little bit of a weird thing. You've got to view it from the top. So what I'm going to do is I'm going to do one cardinal point example with you, and hopefully you can actually sketch this out. Now, very often on your exam, if they tell you that north is facing up, it's great. That means that you've got what we've got here. Now what I'm going to do is I'm going to start adding in an arrow. Now, arrows are very useful ways of representing vectors, because arrows have got two things which I really dig. And the things which I like about arrows is that you can draw them different lengths, which tells me that I can show a magnitude. Now, I want you guys to start thinking about that. Wow, okay, well, I can picture this magnitude. If I want a big vector, I can just make a really big arrow. And the cool thing about arrows is that they point. They can tell me in which direction I'm moving. So what I'm going to do is I'm going to start working with some vectors. Now, I'm going to choose a nice bright yellow arrow. I've got a starting point, and I've got an end point where the arrow ends. And then what I'm going to do is I'm going to try and figure out where I'm landing up. Okay, well, what I'm going to do is I'm going to actually start rotating around. Now, I hope that you can actually see is that I can change the length of my vector, so that changes the magnitude. Now, what I can also do is I can start to rotate, and I can move around my direction of movement. If I want to go north, I go right along there. If I want to go east, I can go there. If I want to go south, I can go there. Or even west. But now, a lot of you have actually figured out, and I can see this from the guesses, is that if I walk south and east, I'm going to land up somewhere inside here. But I'm not entirely sure how far I've walked. And the how far is how I use my arrow. So I can make it shorter or longer, or I can even rotate it around. Now that's quite important. So if I'm walking south and east, one thing which I want you to remember is that you can walk in between these things. Now, I just want to label these extra little bits and pieces, and most of you have actually managed to figure this out. Halfway between all of these cardinal points is actually another set of cardinal points. Now, they're slightly less important, but they are important nonetheless. So if I draw another cross like that, I can actually tell some additional cardinal points. Now, those are the in-between guys. Now, just a hint is that these cardinal points, these extra ones which I'm drawing in yellow, only apply when I'm exactly halfway in between north and east, or east and south. So it's 45 degrees between my cardinal points, such as northeast over here, and then southeast. Now, a lot of you are wondering, why don't I say east-south? Well, north and south take priority over these. So over here, what I'm going to say is southwest, okay, and then over here, northwest. So you always mention the north or south first. Okay, so that's one way of using cardinal points, or using the points on the compass to show me in which direction something went. Here is a problem. I don't always have a compass, and I don't always know what the whole thing looks like. The problem is that this is looking from the top. This is as if you're in an aeroplane above something happening, and that's quite difficult to picture sometimes. Sometimes it's actually impossible. So how else can I start to do cardinal points, or how else can I use a compass to tell direction? And that's using the following system. This is the bearing system. Now, what I'm going to show you is how to use and calculate bearing. Now, the bearing is the degrees or degree clockwise from north. So what do I mean? If I start out from my northern cardinal point and I rotate clockwise, just to remind you which direction a clock goes, most of you guys know, okay? Clockwise, if I start at north, if I move to your right and I start rotating around. So let me just show you. What I'm going to do is I'm going to use an arrow and I'm going to rotate around to get the bearing that I've shown you here. So you start on north and you start to rotate, and I'm rotating clockwise. And I hope that you can see that I'm moving in one direction. So what that tells me is that I've moved through a number of degrees. And that measurement of those degrees is my bearing. Now the way that you write this is not degrees clockwise from north. What I've got to write down now is I've actually got to write down what's going on from north. How many degrees did I count? Now, I've chosen a couple of examples here, so let's just practice with the bearing system. Now, the bearing system is the only way which is used by many navigators. If I'm starting from north and I've rotated around, I hope that you can actually see is that I've gone through a full half circle. Now, a bearing number is always 3 numbers, even if there aren't 3 numbers, and I'm going to show you what I mean by that. So I'm going to say that this first one has got a bearing of 180 degrees. It's just like a normal angle. But what happens if I've got an angle something like 90? So what I'm going to do is I'm going to do a bearing of 90. And I'm going to show you exactly how to do that. So here we go. Let's make one which is exactly 90 degrees. So that's a separate bearing. Now, if you are a navigator, very often what you'll actually see on the compass instruments is they've actually given you an extra number. And sometimes this identifies that you've actually got a bearing. Okay, and over here, we can say that it's bearing 090 degrees. Now that's just 90 degrees with an extra 0 on the front, which is not changing the number. It wouldn't be wrong if you said 90 degrees, but usually the instruments which tell you bearing will actually give you 3 numbers. So if you see 3 numbers, that's what it means. So a bearing of 90 degrees or 090 degrees is absolutely fine. So when I've got my bearing, just a reminder that I measure from north. So let's just take a look over here. How is this a bearing of 135? Let's actually move around with my arrows and let's find out how we can do this. So if I start from the center, there we go. If I rotate round, what I'm actually going to find over here is a bearing that I've rotated all the way around from north, and I've rotated down to an angle of 135. Now, you're going to need a protractor to be able to measure this direction. And this is just a little bit of a hint on how to solve our challenge question for today. So I'm not seeing many of the people answering on the page correctly yet. And here is a little bit of a hint. It's not 135, and it's not southeast. So that's starting to narrow things down a little bit. I want you guys to explain, though. So I've figured out what I'm doing with my vectors and my direction. Just a reminder, with a vector, I can change the length of the arrow, and I can change which direction it points in. That gives me a magnitude and a direction. Now, I've just shown you a couple of ways of giving your direction. There's many, many different ways of giving direction. Things like up, down, sideways, towards something. And the way that I do that is, this is called relative direction. Now, relative direction is something slightly different, and it's something that you and I are actually much more used to. I don't walk around all day wondering where north is. What I do is I say, okay, we'll walk towards something. The way that I usually give directions is I say, okay, we'll travel to the road until I reach something. I travel towards that shop. I turn left at that particular house or that particular color wall. That is an example of how to use relative direction. I'm saying towards or away from another object. Now, here we go. We describe the direction in relation to the object's surroundings. So I say, okay, well, I'm going to walk towards Katleho, or I'm going to walk backwards towards what's behind me here, and that's a desk. Now, in both cases, I've referenced something around me. Now, those are my surroundings. So here we go. So I say I'm traveling 80 kilometers towards a tree. Now it's a bit of a weird or silly examples, but over here, I've given you a magnitude, I've given you a unit, and I've told you a relative direction. Now the nice thing about relative direction is it's easy to understand. Examples of bad relative directions, if I say, well, okay, I want all of you to travel 1 meter towards the right. The problem is that there is no single right. My right is different to your right. I'm holding out my right hand, but it looks like the left on your screen. So you're saying, okay, well, do I go towards that side of the screen, or do I go towards my right? Who's right? The question is there something relative? Is there something absolute in the room? Okay, well, I could tell you all to move 1 meter towards the screen, because that way we're much more awesome. Okay? Absolute or relative direction is probably the most important thing that they're going to be using. Now try use another object in your description. It's going to get you very far. Okay, so let's move onwards a little bit. Something which I just want to point out is that there are certain things which can only be vectors. And here's a couple of examples, and I'm going to deal with some of these today. Okay, force. Measured in newtons, I've got to say where I'm pushing something. It's absolutely important. If I'm trying to lift something, I cannot push it down. I cannot push it forward. I cannot pull it towards me to lift it up. Force has to act in a certain direction. Displacement, which is also measured in meters, well, where are we going? The question is, what is the difference between displacement and distance? And we're actually going to show you on the floor. I've drawn all over the floor, and that's going to happen after the ad break. What about velocity? Now, velocity's got a unit which I'm going to show you, and you've seen this before. I hope that you recognize that meters per second is a way that I can measure speed as well. Now, what makes these vectors? Well, I've got to give them all directions. Every single one of these has got to have a direction. It's very, very important. When I give them in answers, when I ask questions about them, if I give you a vector, you'll know it because there's a direction attached to it. Well, let's start actually working with these vectors and scalars, and let's see if there's any relationship between some of the scalars and some of the vectors. Now, just a bit of an exam hint for you grade 10s. Very often they'll actually ask you to separate scalars from vectors. They'll give you a whole bunch of quantities and ask you to say, okay, well, this one's a scalar or this one's a vector. Now, all of these scalars are scalars because I can only describe them in terms of magnitude, and I'll give them a unit, but I cannot give them direction. If I can give any of them direction, what that makes them into is into a from a scalar into a vector. So what I'm going to do is I'm going to do exactly that. There's a couple inside here. If I add a direction to them, it actually makes them more important, and it actually makes them much more easy to understand as a vector. So let's just see which ones those are. Now these two guys have got partners. Distance is related to displacement. Now the difference is that if I want distance to become displacement, I need a direction. Once again, speed can become velocity if it's measured in meters per second and it's given a direction. So distance once again was measured in meters, displacement also in meters. So they've actually got the same units. They're both measurements of the length of something. What about speed? How do I change it into velocity? Well, both of them have got this unit of m/s. Now, I'm just going to drop this because a lot of people are probably going to be asking this. Or you can say m dot s to the power minus 1. Those of you that have done exponents before know that seconds to the minus 1 means that second goes down to the bottom of that fraction. So I've got distance. I can change it into displacement if I give it a direction. Speed, if I give it a direction, it turns into a velocity. Absolutely important that you know the difference between a scalar quantity and a vector quantity. Now, what I wanted to do was to just highlight a difference between distance and displacement. Now, we're going to do a little bit of a demonstration after the ad break, but I just want to lay down the groundwork first. So now, I can walk a distance of 2 meters. Now, the problem is if I try to walk 2 meters towards the wall or out of the shot over there, it's quite important where I'm walking. So distance actually becomes quite limited. Most of you actually have been doing this before, and it doesn't actually tell you where you want to go or where you've gone. So distance over here I actually find quite useless unless I need to know how far I've actually gone. Because distance is what uses up my energy very often, and it's what uses up the petrol inside my car. And what I want to do is rather I want to describe this as a displacement. So what happens if I add on a direction to a distance? This might seem very simple, just take distance and add on a direction and that makes it into a displacement. That's not actually all that true, and I'm going to show you the difference between that. But over here, we've got our magnitude, we've got our direction. Now all of a sudden this means something. I know, okay, well, I've got to travel 2 meters east. Now one of the things that I haven't actually put here is that displacement doesn't actually tell you how you got there. So now I'm just going to put this down here. So it doesn't matter how we got there. So now the question is, why are you saying it doesn't matter how? Well, displacement only cares about the result. What is the result of what I'm doing? Where did I land up? Well, here's my question to you. What is my displacement for the entire day? So at the beginning of the day and at the end of the day. Well, I started at my house and I went to school, I taught classes and I came back. I traveled a great distance, but I didn't travel a great displacement. So what I'm going to do is I'm just going to give you a little bit of a squiggly path to think about. Now, if I decided to give you a little bit of a route map from the top, anyone that's ever played with a mapping program or has played with the GPS has seen these squiggly lines before. You can travel down 1 block, you can turn at the 1, you can go down the bottom, you can end up at your favorite restaurant, you can eat your McDonald's, and you can travel up, and you can go to the bookshop, and you can land up there. So if I start out in one place, and I end up in another, I want you to be able to tell the difference between the distance and the displacement. What I'm going to do now is I'm going to tell you. Here we go. We've got our distance. So what I've done in white is I've shown you the distance. That is a collection of all these little paths that we traveled. But now if I want my displacement, it's something slightly different. Displacement asks, where did I land up and in what direction? So let's draw in what is the result from start to end. So let's do exactly that. I'm going to choose my nice arrow because now I'm dealing with vectors. So where did I start? Well, I went down there, then I started traveling down there, then I started traveling down there. You can see that my end result is actually quite different to the distance which I traveled. So the difference between distance and displacement is more than just the direction. Displacement is measured from the start to the end. So let's just make a note there between the distance and the displacement. Displacement doesn't care how you got there. It doesn't measure the individual paths which you take. The displacement is just from the start to the end. It doesn't take into account the distance. Okay, I think people are probably begging for an ad break. What are you thinking?
I think they're actually enjoying it, but maybe we should be nice.
Perhaps. Guys, please take a short rest and be back with us.
Yes, of course. You know that the lesson gets even more exciting, as Phil has said. So do not move from your seats. I mean, don't even go get a glass of water. Just stay there because we will be right back. See you now. Welcome back, Mindsetters. I hope you guys really didn't move off your seats. I am loving the answers and the interaction on the page. I'm glad to see that you guys are actually awake and present. It's very refreshing. Over to you.
Okay, well, welcome back, guys. I can see that you guys are listening very, very carefully. I saw that Southeast comment kind of really through a few of you. What I'm going to be doing now is I'm going to be showing you on the floor how to tell the difference between a resultant and the individual pieces which go into it. Some of you are asking what the difference between a resultant displacement and a displacement are. I'm going to be talking today mostly about the resultant displacement. Now, displacement usually is a resultant. Now, I'm going to show you what that means in a second. What I've done on the floor is I've actually drawn out 2 different ways of getting to the same place. So I've got a start here, which is down here by my feet. This is where I'm going to begin. Now, what I'm going to be doing is I'm going to be moving in 2 different directions, and that's exactly what I've done in the challenge question. So I'm starting here by the start, and we're going to be moving in one direction. Now, I'm going to start with a solid line, and I'm going to go in a direction. I'm going to use this as an indication. Now, what I mean by a resultant is what is happening at the end of everything, once everything has been taken into account. So if I use the word resultant, it means everything together. So what I'm going to be doing is I'm going to be moving from my starting place, and we're going to be moving 1 meter towards the other side of the shot. So what we're going to be doing is we're going to be taking one step and we're going to be landing up here. But what I'm going to do now is I'm going to add to the distance. I'm taking another path. Notice how I used the word distance. So I stepped 1 meter, but then I moved 1 meter in a certain direction. See how I've got an arrow down here on the floor? That means that I've moved with a vector quantity. So now it wasn't only distance, but by giving it direction, I made it into displacement. So what I'm going to do is I'm going to move another 2 meters in a certain direction, and we're going to see where we end up. So let's move our 2 meters in the direction towards you guys, and I see that I've landed up at the end. Now the question is, what is the resultant of what I've just done here? Well, I'm down here at the end, and what's happened is I've moved from my start over there, and I've actually moved down to the end. The question is, how did I get here? Well, I moved 1 meter, and then I moved 2 meters. So I've moved a total distance of 3 meters. But now here's the question. How do I get the displacement or the resultant displacement of what I've done? To do that, I've got to go right back over there and I've got to go right back to the start. So let's do exactly that. So I've got my start here. What I'm going to do is I'm going to show you my displacement. An easier way to get to the end would have actually been to go straight down this dotted line towards the end, from the start to the end directly. And that is my displacement. The difference between distance and displacement is that I would have to travel 1 meter, then 2 meters. My resultant is going to be slightly shorter than the total distance, and that's generally always the case. The resultant is the immediate distance from start to end. Sometimes they call that as the crow flies. Now, if you want to go to the other side of a block, the easiest way, if you had wings, was to fly over it just like a crow. So when they say, as the crow flies, that means that I'm going directly somewhere. What I'm going to do is I'm going to go back to the board and I'm going to show you how this works with our challenge question. A lot of you guys are really, really racking your brains and you're really struggling. What I'm going to do is I'm going to go right back to the beginning of the show and we're going to use our challenge question. So let's go back to it and let's put you guys out of your misery and let's figure out what goes on here. Well, some of you actually managed to figure out that I'd left out a unit. Remember, I told you guys that we'd left out something inside the 1, and that's very good. Most of you managed to figure out that I had to say 30 meters. Now what I'm going to do is I'm going to help you figure out what's going on in the challenge question. Some of you have got the right answer, and you've actually managed to figure out that I'm using a vector. That means that I've got to use an arrow for each one of these quantities. So let's make a little bit of space, and let's see how we can go 40 meters south, then 30 meters east. So what I'm going to do is I'm going to grab my handy arrow. Now, you guys don't have this tool at the home. So what I'm going to do is I'm going to do this very, very slowly, and I actually want you to do this with me. Now, the question is, how big should I make my arrow? Well, here's the answer. You've got to choose an arrow which reflects your vectors all the same. So what I recommend that you do when you're drawing vectors, and this is a very good lesson to learn, is to choose a scale. Now, a very good scale for something like this might be, so, well, if I'm going to choose a scale for this, well, I've got to represent 40 meters. Now, that's a very big piece of paper. I cannot stretch out over half a rugby field to work out a vector question. So how do I make that slightly smaller? Well, you can start off with something quite simple and say that, 1 centimeter is going to give me how many meters? Well, you can actually decide. So what I can say is that, I've got my 1 centimeter. Let's measure out, we can do 4 centimeters if you like. That means that 1 centimeter equals 10 meters. So now the question is, how do I represent these other vectors? Well, I've got 2 arrows, and these are a bit of a problem to represent. So now what I've got to do is I've just got to make a bit of a shopping list. I just want to make sure that everyone knows what we're doing. We're going 40 meters south. Then what we're doing is we're going to go east after that. We're going 30 meters east. Well, okay. So now we've got some information, and I've chosen some cardinal points. Well, the way to start these questions is to draw the cardinal points. So let's do exactly that. So I'm going to draw a set of cardinal points over there. There we go. And we're going to start out here. So now what I want you to do is to draw with me. Let's make sure that we've got enough space, and I want you to draw this exactly with me. So let's start out by saying we've got an arrow. Let's actually make that into a different color so that everyone can see. There we go. Whoops, we've actually made our background. Let's go back to there. Okay, so let's make a little bit of space over there. Let's get ourselves a blank page rather. Otherwise nobody can see what I'm doing. Okay, so our vectors with arrows, let's start off with our cardinal points. And let's actually start to go south. Let's make it green so we can use our yellow arrows. That makes life nice and simple. Okay, so starting out with our cardinal points of north. Let's start using our arrows. The question is, how long did we choose our arrows to be? Well, if 1 centimeter gets me 10 meters, how many centimeters would get me 40 meters? Well, let's do this. 1 is to 10 as something is to 40 meters. Well, I hope that you can see. All that we have to do is we have to figure out how to use our ratios. So let me give you a little bit of a tip on working with scales. I want you to write them exactly like this. And this allows me to do something quite cool. So I want you to split your ratios into 4 pieces. Now, it depends on where you're starting from and where you're going to. So I'm starting with 40 meters, and I want to get into this question mark block. Now, most of you guys have been working with the triangles, where any time you go over this line, this horizontal line, that means to divide. Anytime I go sideways, that means to multiply. So I'm going to write that in green. So now when I go from 40 to 10, I'm going to divide. So I'll say 40 divided by 10. What does that get me? That gets me 4. Then I multiply across 4 times 1, and then equals at the other side. So I've actually gone around like this. So I divide, then I multiply, then it equals, and what I land up with here is 4 centimeters. Let's just make sure that's nice and neat. I'm making a bit of a scribbly mess over there. So what we've got to do, there we go, 4 centimeters. I'm going to go through this again in a short moment. Don't panic, we've got to do another one for our other unit, for our other quantity. So now, how do I represent 40 meters? I start off on my cardinal point right in the middle. So let's do that. There we go. So we started off with a 1. I've drawn a line, which I want you to draw this out with the ruler. Let's just make sure that's out the way. And that's 4 centimeters. When you've drawn a vector, it's always a good idea to mark it with the exact amount that it represents. And that is 40 meters. Now, on your page, that's just going to be 4 centimeters long. The question is, where do I go from there? I've started over there. I've ended up at the end there. And I've ended up 40 meters south. So I've gone south. The question is, now, do I start back from the beginning? No. I've traveled south. Now I can travel east. So let's do our ratio again. Let me show you how to do this ratio. Okay, so once again, I've got 1 centimeter to 10 meters. And we're going to draw our little cross over there. And we want to now make 30 meters. How do I make 30 meters into centimeters using our particular scale? Now, this scale is very, very easy. I'm sure that most of you have actually managed to figure this out without thinking too much. But I want you to practice this method. It's very useful for any ratio that you come across. You put your ratio at the top, and then you put your unknown next to your known. So I know that I've got 30 meters. So I divide by 10. I multiply by 1, and I land up with a different result. So that's divide. Then I multiply to go across. Then I say equals, so I say 30 divided by 10, multiply by 1, gets me 3 centimeters. Okay, so let's put in our last vector. I know that I've got a 3 centimeter line stretching out in that direction. Now, lots of you are saying, okay, well, that puts me southeast, and that is not true. What I'm showing you is that I've got 40 and 30. Now, if I draw in a resultant line, what I'm going to actually do is I'm going to connect this. A resultant displacement over here. Let's draw that in with a green pen. Okay, this displacement is what I'm after. Now, I think we're going to run a little bit short on time, but if you work this out using Pythagoras, what you'll find out is that your displacement over here from start to end is actually 50 meters. So I do this by Pythagoras, and that gets me 50 meters. Now, it's not southeast. This is not southeast. Southeast is around about over here. The question is, how do I get the true direction? Well, you can do this by measuring on your page if you're absolutely accurate. What you'll find is that you can measure around right from the beginning over there. and you're actually going to find out that the correct answer is actually B. So let's just go back to that and discuss what that bearing is. There it is, a bearing of 143. Here we go. That is our correct answer over here. So if you selected B and you explained yourself well, that might mean that you get a calculator. Doesn't mean for certain, but if you got there first, that's great. A bearing of 143 was the correct answer, and you had to actually measure that off your protractor. Now, just for reference sake, a bearing of 135 would be southeast. Please make sure that you get that right. I think that's around about all the time that I've got to explain vectors and scalars for today.
I think that was awesome, and I know that the learners really enjoyed it, Phil, because they said they enjoyed it. So thank you very much.
Sure.
And thank you, learners. You guys were absolutely amazing today. And remember, help each other on the page, even when we're not there. Just make sure that you explain everything fully. It was such an awesome show, and I hope to see you guys for physical science next week, Tuesday. Thank you again to Liberty. Liberty has been absolutely awesome. See the grade 11s next up for physical science. Bye, grade 10s.